Really nice
So,
to.
oh,
Oh,
no, go for it. So our guest today is Georgia Channing from Hugging Face. Georgia is the ML for Science lead at Hugging Face and a DPhil candidate at the University of Oxford. Her academic background is in machine learning, and her research has spanned neural architecture search, protein classification, deepfake audio detection, and hyperspectral imaging. It seems to me as though there's absolutely nothing that she can't do. She holds an undergraduate degree from the University of Tennessee and a master's degree from the University of Oxford, and she now works on building tools and methods to advance scientific achievements. So it's a great pleasure to have her join us. Thank you very much, Georgia.
yeah, thank you all for being here. I apologize for the hard stop. It wasn't planned this way. I was supposed to be back home in the, comfort of my office. But if there's any like loudspeaker things and you don't hear what I say, please feel free to either interrupt or just message in the chat, and I'm sure Rohan will figure it out. I am gonna get started. And let me just figure out how I do that. Okay, can everybody see my screen?
Looks great.
Yes. Okay. So already had a lovely intro, but yeah, I'm the AI or ML for Science lead. I think I change it every other email that I send at Hugging Face. I just want to before we get started, I've given us like 3 slides of primer on what Hugging Face is for people who don't know. And the reason that I bother doing this is because there's a bunch of questions that I always get asked, but also because I think it gives you a better sense of like what I sort of represent in the ecosystem. As this talk will be a lot about how do we engage, how do we optimize the ecosystem, how do we make progress as a community faster. And I think it's meaningful to know what role we play in that. Um, Let me figure out if I know. Okay, here we go. So, why is it called Hugging Face? That's our first FAQ. It's because it was started in 2016 as a chatbot company, and so it was supposed to look like a friendly chatbot. Then ultimately, ChatGPT became a thing, as we, all know and use. And so Hugging Face sort of pivoted, and our chief science officer made this library called Transformers, which allowed people really for the first time to sort of like say import model and then run. So that like the machine learning community has been open source and open science for a really long time. That's part of the reason that we've made so much progress in the last 20 years. But that used to be like a lot of like different disparate libraries and GitHub repos, and you would look at a paper and you would try to reproduce their results. And all of those things are really meaningful and good. And I don't mean to be disparaging about that at all. But what our CSO did was basically make the building blocks so that you could make any model without having to reinvent the wheel from scratch every time and be like, how does this person import modules? How do they build their layers? That kind of thing. So sort of diverse. And like what's the knives with many, many tools? Um, Sorry, I'm forgetting English. I'm a bit tired. But maybe it's a switchblade. No, it's a the things that have like so many tools, like 9 different things come out of them. What
Oh,
is that called?
Swiss Army
Yes,
knife.
a Swiss Army knife. Yeah, exactly. Yeah, exactly. Okay, thank you all for bearing with me there. Um, it's used all over the world by many, many production teams and things like that, but also research groups and just hobbyists. Some of the coolest stuff that I've ever seen built was made by a 15-year-old from rural Turkey. And it really just, Hugging Face's vision is to empower the community in general. And that, means servicing like the biggest people like Meta and Spotify, Novo Nordisk, but also, 15-year-olds. There are now, I don't know if this is yeah, no, this is correct. So there are 2 million open source models on the hub, and there are more than 500,000 data sets. So that's a lot of stuff. Obviously, not all of it is gold, but a lot of it is, and a lot of it's really great. And here we have stuff that's very focused on large language models, but in the last 6 months or so since I started Hugging Face, we've spent a lot of time and energy trying to make the hub more friendly for science. So supporting people who are doing, say, fusion engineering or biotech, like antibody developability, materials generation, stuff like that. Okay. How is it free? What do we make money from? It's a freemium model. It's just 99.9% of users are in the free tier. And people like Meta or Novo Nordisk who say like want to manage models across like very international teams with different levels of access management, and they want to integrate it with their, Okta, all that stuff. They pay for things so that the average person doesn't have to. I think it's like worth saying that I think Hugging Face is underutilized in the academic community because like you can store 100 terabytes of private data for free and it's unlimited for the amount of public data that you can host. So you don't even like need grant money. You can just put it there. And same stuff goes for models, things like that. So those are not typically as big. Michael's looking really skeptical. I'm loving your facial expressions here. But it's true, and you can go look on our page. Okay, now science. Primer over. So over the summer, I and a coworker of mine, Abhijit, who is one of our policy leads at Hugging Face, wrote this paper called AI for Science, or AI for Scientific Discovery is a Social Problem. And now you might be asking, I'm in the Toronto Data Workshop. Why are we not talking about data? How could it be that all of my scientific problems are actually social problems? And so now probably not all of your scientific problems are social problems, but a lot of them are hard. A lot of them are. And I think it's worth naming what those problems are so that people can think about solving them. I think that 80% of solving a problem is figuring out what the problem is. And so, we'll get to go through all of that in this talk. And then at the end, I also have some good technical problems that I think actually make, say, achieving scientific advances really difficult with the tools that we have now, which are obviously really powerful, lots of other things. So here are basically I think, four main offenders. One is the AGI scientist myth. So obviously there's a lot of AI scientists out there, and I'm not trying to say that those have no utility, but I think that there's a lot of well, I'll get into it a little bit more in the slides. I don't want to spoil it here. Then two is suboptimal incentive structures. I'm sure that this is like not a surprise to anyone, but lots of things that you get rewarded for are not actually things we want to reward. And that is creating good incentive structures is really, really difficult, both in reinforcement learning and in just regular people life. Three is goal misalignment. And there I'm talking really specifically about the differences in the way of what problem solved means depending on the community that you come from. Basically, like if you're coming from a machine learning background, a computational science background, or an experimental science background, and the gap gets bigger and bigger between these three groups. And then lastly, communication issues, which never sound sexy, but are the root of a lot of missed opportunities. And so I think it's worth talking about in two particular sort of faux pas that each community makes that makes it really, really difficult for them to engage with the other. So also there's going to be a lot of XKCD in this. I just want to warn you now. But if you get bored with what I'm saying, feel free to just peruse. So the first thing is that there's a very common narrative that I hope is slowly going away, but I'm not sure that it is, that AGI is looming and it's going to be able to do everything that we wanted to do. All the jobs will be replaced. And that also means that all of science, like scientist jobs, will be replaced because we'll know how to do science now. And so we should only work towards that because ultimately, once we have AGI, then all of our other problems are solved, right? The thing is that there's a couple of reasons why this doesn't really work. Just before we even try to define what is AGI and whether or not we're going to get there, because that's could be the subject of a whole talk series itself. But the first thing is that the point of science is to understand things, not outsource our understanding, right? So most scientists are in general not very interested in black box answers to things. They're not interested in an oracle. An oracle is useful, but that's not the purpose of science. And you can read sort of the philosophy of science and the science of science. And really the whole point is to empower humans and allow us to really understand how the world works rather than just predict some outcome. Now we can have a maybe philosophical debate about if you can always predict 100% of the time what's going to happen, then do you understand it? Chinese postman kind of problem. But we're a really long way from that. Second is that science, very broadly, right, is harder than autoregressive text rollout. Now, what do I mean by that? One example is that if you say look at the last 5 words that you saw and you were asked to fill in the next token, right? So the way that an LLM generates content, you would do a pretty good job because actually the English language and many other languages are really quite limiting after you've only seen once you've seen 5 grammatically correct words, there's really not that many options after. When you think about AlphaFold, something that is structurally extremely similar to the way that large language models work, like a context window of 5 doesn't get you anything. A context window of even 2000 might not even get you into a specific protein family, right? So like the amount of context that you need to do a problem that's theoretically super similar, right, is much, much larger. And that's like, really on the same order of magnitude of complexity theoretically. That's before you add in all kinds of other data and sort of like more difficult scientific problems. And then lastly, it's like the first two things that I've talked about are maybe like, okay, this is a waste of time, but they're not like, oh, this is making things worse right now. Whereas the last thing is that when you go around saying, well, we're going to replace all scientists, you can imagine that scientists are not that psyched about that. So when you go want to work with scientists and you're like, oh, I really want to like work with you so that I can replace you, like they're not that keen on it. And you'd be surprised how frequently people do that anyway. Um, which is just, I think one really low-hanging fruit example of how scientific problems are really social problems. Um, Next, suboptimal incentive structures. So I am in fact a PhD student, but just imagine that like, if you're not one of these things already, that you were. And you can have two choices. I know there's a bunch of text on this screen, but basically choice one is, I think, honestly, what most people do and what I have also done in the past, which is, okay, I want to advance my career. I need a paper. How do I get a paper? Okay, the way that I get a paper is I like look around for some way that I can come up with some cool new methodology that I want to show is better at something, right? So that's basically your criteria for this will probably get published. And you want to do like a reasonably good job. But so in order to execute on this, what you do is you look around for like a data set that you can just like ideally plug and play, make it really easy to load. And then you're going to try your methodology and you're going to tinker with your methodology until it performs better on the data set that you chose. Right. And then you're going to publish, and then you're going to publish that paper and you'll be like, look, we did so great on this little data set. Um, and then next time that people publish in the same domain, they're going to cite your work and you're going to be like, yay, my H index goes up and I'm going to get faculty positions and I'm so happy. Okay, that's option one. Option two is, okay, I want basically to do something really useful. I like really want to understand how this works. I'm gonna make a robust model. I'm gonna benchmark it across tons of different data sets so that I understand to make sure that it works in environments that I don't expect. But oh no, all of my data sets are all over the place. All the data is in different formats. So now what you're probably gonna do is spend multiple weeks putting all the data together in order to just test your one hypothesis, right? Um, and that is not very appealing if what your goal is just to like try papers as fast as possible, because like that is a kind of waste of time. Um, Especially if it's not ultimately required. And now ultimately you're going to give yourself a much harder problem because you're evaluating on much more data. And so your model is less likely to, beat the benchmark that you've set. And so maybe you don't get a paper out of it because your methodology is not more clever than the one that came before it. And so what most people do is choice one because you get gold stars, right? But actually, this is really not useful to the community because probably next month somebody else will also make a model that is slightly better on some data set that they have somewhat arbitrarily chosen. Whereas you could have really actually helped the field by doing a whole bunch of grunt work that nobody wants to do. So this isn't meant to be a personal condemnation. I've definitely existed in choice one before, but it's really a reflection of the fact that the incentive structure is bad. And so what we should value, or we should try to value, encourage people to value, are these kinds of things where actually, yeah, like you spent all of the effort to put together 100 different data sets. And now maybe that means that you're a pandas expert and maybe I'm not a machine learning expert, but ultimately, you can write blog posts about these things like, ICML is not the end all be all of, all of civilization. And we should, as a community, start caring more about these things because ultimately that's what helps us all, rather than like getting stuck in lots of local minima where everybody goes off onto their own little side project in order to get credit for it. Okay, then there is goal misalignment. Sorry, I'm just checking our time here. Most machine learners come to problems and they say, okay, I have some data and I have a metric. I think that fundamentally, actually, that's how most machine learners experience most problems. And now, how do I minimize the metric given the data that I have? And in most machine learning, we talk about scaling a lot. Having a lot of data is very good. We like that. Um, but the thing is that most science is not unlimited data, and the objective is not like cannot be evaluated by a single metric. That's very rare, in fact. And so most scientists come to problems and they say, okay, I have these resources, say like, you work in material science, I have all these samples of graphene and things like that. What can I learn from this data? Right. And that's a much, much more open-ended question than the first one. The first one is like, okay, now let me engineer, let me toolkit. And the second question is, you know, like it could be anything. And any individual scientist that comes to that problem is going to come up with a different set of things that it could be. Um, and this gap is so there's the machine learners who are like, on the far end of this. Now, if you think of yourself as a kind of machine learning person and you're sort of like offended by this, but maybe you have some domain expertise, like I might consider you, say, like a computational scientist. You might exist somewhere along this spectrum. Um, and those people often like, there is an explicit goal. And maybe you don't have just one metric for it, like, your classification accuracy, but you have like a pretty limited set of this is what computationally good outcomes are, and this is what my data is, and I can, sort of choose from this like rotating thing of, it would be great if we were better at, say, predicting the shape of binders, and there's only a couple metrics for that. And then, yeah, eventually you have to test these things, but that's like a ways away, right? So you're not really too worried about that. Whereas I will say, here we go. Oh, no, it's a different one. Sorry. Hold on, let me see if I go back. Nope. Okay. Sorry. I was going to tell you a story, but I did recently interact a bunch with a like really quite successful and famous material scientist, like experimental material scientist, who I was trying to get to work with Hugging Face, and this exact goal misalignment thing played out exactly, which was really a shame because in fact what happens is like this person has tons and tons of resources and tons of data, and they're like, oh, I'd be interested in this question, this question, this question, this question could be cool. And then the machine learning person is like, okay, yeah, but what is the one problem that we're solving where I can reduce this to one number? And if you don't have the answer, most machine learning people lose interest. And that is not a necessarily science problem. It's like also a machine learning problem. Like we need to be more yeah, I guess open to basically questions that are not just like, now what is my, what is my loss? Yeah. Okay. And then lastly, we have our communication gaps. People are just not very nice or good at talking to each other. And people, I think, can be quite demeaning, particularly in machine learning, where people often will come to a scientist and say, I'm going to solve all your problems for you. And then, to be fair, the scientist then, shows you 120 slides, and you both throw up your hands, and then everybody leaves. And that I can tell you an anecdote, which is that my understanding is before DeepMind approached CASP to try to compete with AlphaFold, the Meta team approached them first, but they didn't want to work with CASP. Like they weren't actually interested in working with the domain scientists. They were like, just like, give me the data and like we'll talk to you in 6 months. And nobody at Meta has a Nobel Prize in chemistry. Anyway, so maybe not nobody. I mean, probably nobody. I'm not knowledgeable enough about the Nobel Prize in chemistry, but I'm pretty sure. Anyway, and so my point is just that these things happen even like very, very high stakes. And mainly the point is to try to be more patient. I want to take a moment to highlight this particular XKCD, which I think is really, really true. And I've had lots of conversations like this. I won't read it aloud for you. I'm just going to ask you to direct your attention there for a second. But yeah, it's just so good. Because I also don't even know what olivine is. And I have a lot of conversations like that. And so I think that yeah, just again, being more patient, and being willing to explain things from first principles. And this is really non-trivial because what will happen is somebody tries to explain something from first principles, and then they'll give you 120 slides because they're like, I'm going to show you everything that I've ever thought in the last 6 months that might be related to this research project, which is unfortunately not a very good way to actually convey information because people get overloaded really quickly. And what happens is that having been given a number of slide decks myself, I, having no domain expertise, am now required to decide what is important basically on the fly. So I've been given a huge amount of information that you didn't want to synthesize because synthesizing it was hard, and now I need to synthesize it, but I'm far less qualified to synthesize it than you were, if everybody followed that. Yeah. So I think that's a very common problem. And I think that, yeah, like again, it's one of those things. It's like, like try harder isn't the answer, but just like trying to figure out when you're in a situation where like the onus actually is on you to figure out what's important and convey that to somebody else succinctly. And then try to actually do that rather than being like, they'll figure it out because like probably they will not. Um, Yeah, the flip side of that is people in the machine learning community should not try to make everything a transformer problem. And this is basically the situation that happened in Meta, right? Where it's like, I have this crazy tool, you're gonna give me the data, and then I'm just gonna like magically figure it out by putting it into a transformer. Doesn't really actually check out most of the time. And sometimes it does if it's really similar, but even in AlphaFold, right, which is very, very similar because it's a sequence to sequence problem, to say like, generative text modeling. Um, it was still really difficult. And most scientific data for the scientists out there is not sequence to sequence. And I'll talk about that in a second in our technical issues component. But the two main findings that we have in the paper that we wrote is that people should really stop making custom data formats. They're really, really unhelpful and difficult to work with. Um, and it makes cross-domain work much, much, much more difficult. So again, I will direct you to the XKCD, which is just really to say that we're going to do one way of like recording this. And we should get rid of all this other stuff. And definitely way more than this number of dating styles exists for cataloging scientific data. I don't know if you've ever looked at the PDB, but the protein data bank, if you want to download a file, it'll give you like 12 different options for different file formats that you can download it as. Now, why do they do that? Because they really care about having people be able to say, like, go from exactly wherever they're at, like trying to smooth the operation for them. So no matter what's like data type your software takes in, they will provide it for you. But this whole thing would be way, way easier if people just put things in CSV or Parquet. Like really almost everything can be CSV or Parquetified. And the fact that we're not doing that is a real shame because actually what it means is that like PhD students all over the world are taking like weeks of time in order to like reparse data to put it all into one format. And I can say that I just, like spent the last week like writing a parser for the hub, like for the Hugging Face hub that will read CIF files, so materials files, and FASTA files, trying to like expand the different number of data types that we can support. But FASTA files in particular are just like it's text files with like 3 rows, like with, like protein sequence quality space, protein sequence quality space, protein sequence quality. Like, why is it that we need to have, why couldn't this be in a table? And the answer is that it probably should be in a table. So anyway, people should stop making custom file formats. And then secondly, this is the problem with the sequence to sequence stuff is that like most scientific data is really highly dimensional. It's particularly true in the health domain, but if you think about physics where you have these absolutely astronomical measurements of like, it's like 40, like dimensions, like 40 by 30 by like 275, how do you even tokenize that? It's really difficult is the answer. And like people try, but part of the reason that these things don't work as well as like autoregressive text rollout, which you see in the top window in the top box here, is that I don't know how to flatten this. And if you think about like omics data, which is very like common in cancer treatment, right? So what you'll have is a TIFF file that is a piece of like prosciutto of human skin. So a super, 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 super skinny piece of human skin that they put between a plate and then they stained. And this single image, which is probably something like this size, will oftentimes be like a gigabyte by itself because it's so incredibly high resolution, right? So loading the things is difficult to begin with. And then each cell in the image right, will also have like a long vector array of qualities associated with it. So it'll have like a whole list of all the genes that are in the cell that are being expressed in the cell. And it may also have information about the staining and about the quality of the genes and whether or not the DNA in them is being expressed or they were healthy or like all of this kind of stuff, right? So, and there's huge spatial relationships here. How do you put that into a token that you're going to put into a line? I don't know. I don't think anybody really knows the answer to that. But it's a really difficult problem, which is part of what makes it so frustrating when, say, machine learning people come and they're like, I'm going to solve all of your problems with my tokenizer. And it's like, your tokenizer has never even seen like, Urdu language data. How is it going to deal with this? Um, okay. So the takeaways basically from this, is that there are lots of things that are, sort of problems that we can day to day help solve. And I think that there are a lot of, and the reason I think that this matters is because I think that there's a lot of, talks and there's a lot of rhetoric out there. It's like, oh, we don't have the data, we don't have the infrastructure. I don't know if you guys saw, but Anthropic dedicated 50 billion or something crazy today to building like US training infrastructure, which is great. But most of us cannot really participate in that. And there's a lot of things that we actually can help change, but just by trying to like be more patient and have sort of a better understanding of where other people are coming from, essentially. And I hope that I have shown you a bit in this talk where some of the biggest divergences are, and how we might combat that. So yeah, questions.
That's wonderful. Thank you very much, Georgia. A wonderful talk. If are there any questions? If folks can just raise their hand, and then I can call on you. We have Georgia for 16 more minutes before her plane takes off. So again, if anyone has any questions, feel free to raise your hand. Georgia, maybe just to start us off with the communication piece. One challenge that I see often is with people using the same language but talking past each other. So, I mean, to use your quartz example, quartz might mean one thing in economics and mean another thing in political science or something like that. Is that something that you came across in your research?
Um, yes, in the sense that I think that people not defining their terms and then sort of yelling at each other is universal. Um, but to be totally honest, most of the domains that people I work with are operating in things that they would consider like really quite niche. And so in that case, the vocabulary is specialized enough that this actually doesn't come up that much. But that's largely to do with the fact that I work a lot more with physicists and biochemists and that kind of thing. Whereas I think that in economics, and more of the social sciences, many more of the terms have sort of day-to-day meaning that might get in the way um, of people being specific and understanding each other.
Wonderful, thank you. So we'll go to Chris and then Nina. So Chris.
And so, yeah, just briefly, thanks for the presentation, Georgia. And I don't want to interfere with Nina's questioning, but just to ask, one of the points that you had made was about the communication gap between domain experts and technical experts. And I'm wondering if you have thoughts on, sort of like technical approaches that try to address that issue. So I know some software development patterns, and we're thinking also about programming architectures. They seem to be aiming at a kind of better integration of domain expertise with technical implementation. And I'm just curious if you've encountered that in your own travels. Thanks for the
Um,
presentation.
oh, anytime, but could you I want to answer your question well. Could you give me an example of the sort of software that you're talking about? The technical
Yeah, so we're
integration? Yeah.
thinking of domain-driven design for
Mm-hmm.
software patterns and ports and
Mm.
adapters or hexagonal architecture for programming architectures. And the real goal of it is to enable a sort of a clearer separation of concern between the things that domain experts are experts in, the language of the domain, the use cases, and so on, and then the technical implementation, and also to make it swappable so that something can change on the technical side, even as the domain model remains constant. And it just seemed to me that it's a nice opportunity to try to bridge exactly the communications gap that I did a great job of identifying, is that people are really kind of talking past each other, and the jargon on the programming side or the on the computing side rarely aligns with the jargon on the domain side, as you pointed out.
Yeah. Um, Hmm. Sorry, I'm just trying to think about a good answer to your question. So this segmentation of work, basically, like of okay, like this is the technical component that I want to use, and like this is the domain question that I'm trying to investigate. I think happens all the time, and I think that that is very good. Um, but I think I'm trying to figure out exactly what I want to say. Um, I think that the segmentation of work happens all the time, and that is useful. But I think that you can go too far into the other direction, where actually, like the whole community would function much better if basically, people with domain expertise, um, interested themselves enough in the technical component, to discuss it. And now that doesn't mean that you need to rebuild transformers from scratch, but in the same way that like you should know how your Excel functionality works, like you should also know how your machine learning functionality works. And I think that the idea that you're going to like abstract all that away is misguided because, in the same way that we think like, for example, people who study biology should understand math, I think that people who study biology should also understand basic machine learning functionality. Um, and maybe one could make the argument that probably not enough bio people did study their math. Like, there are all these like biostats crises all the time, and people can't trust any of the papers they read. But I think that that really goes to reflect the problem that I'm talking about. Um, and unfortunately, the same should basically be true of machine learners. It's just that, like, it's a lot easier for, like, say you're in protein engineering. It's a lot easier to become passingly familiar with one area of machine learning versus being machine learning and being like, okay, I'm gonna be knowledgeable about every single domain. So probably what will happen in the next 10 years, also people will specialize more. Um, but like, the job that I have and that, maybe I'm succeeding at or maybe not is to try to be surface level knowledgeable about like probably like 10 or 15 different domains. And that is extremely time consuming, but ultimately like my work could not possibly be done if I did not do that. Um, yeah, yeah.
Thank you. Perfect.
Nina?
Hi, Georgia. Thank you so much for your talk and just for dedicating the time right before your flight. I realize it might be like a bit stressful, but in kind of like looking at your presentation holistically a little bit, could you speak a bit more to the earlier point about AGI? And like in my head, I've kind of made this link about that communication gap and the really poor interoperability between different domain experts in different fields. Is that sort of a reason why we're maybe not likely to achieve or reach AGI like we maybe thought we would?
Yeah, maybe. I mean, I think that this is like very quickly going to be like, what is AGI? And I think that that's really difficult to define. I think that the gap that like the gaps that I've talked about in this presentation are why we say haven't achieved more in like science with AI in the last like 2 years. Like there've been a lot of headlines where it's like, this is going to revolutionize drug discovery, that kind of thing. It hasn't done that yet. Um, I don't think that that's why we haven't been able to replace white collar jobs. So, for example, like, people who are consultants or they do sort of like, I think a great example actually is like accountants, right? Why is there not an AI accountant? Most people do not struggle to actually understand accounting. Like, this is not the kind of thing where we need to discover something. We just like need to do a sequence of operations really well. And we can't do that. And like, there's a benchmark on Hugging Face for people who do, it's like financial services work. And ChatGPT, with like pro think mode, etc., it's like 15% of them right. And like this is the kind of thing that like, if you were a human and you like spent like a couple hours reading the manual, you could just do these operations over and over again and it would be okay. Anyway, and so I think that that is actually why we're not achieving AGI, rather than the gap between domain scientists and machine learners.
Okay, interesting. Thank you.
You know?
Thank you, Nina. So Mary from the chat asks, what is lost when trying to use a hammer to solve a problem? What do you advise more of within the ML AI space?
Um, Mary, can you define hammer? Do you mean just like trying to like throw a transformer at everything, or something
Yes, it's
else?
regarding your point about the
Yeah.
transformer for everything.
Yeah. Um, well, I guess what I think is lost is that unfortunately lots of people give up on machine learning when they decide a transformer out of the box cannot solve their problem. I think it's great. Transformers work on lots and lots of things, and that's really great. And you only find out if transformers work on things if you try to solve the problem with a transformer, right? So insofar as we're trying to solve lots of problems with transformers, that's useful. But I think that, you know, if people get to the point where they're like, well, this transformer doesn't work for me, then machine learning isn't for me. I think that that's a real shame, and that happens to lots of people. Or even that they try the first generation of a model and they're like, this really doesn't work, and so they give up on all future generations. And I know, for example, that like people who work at Merck, like the pharma company, their computational chemists, got stuff out of like the AlphaFold gem like a year and a half ago, and they were like, well, this is all, I get 10,000 sequences and all but maybe one are garbage. But like a human with a PhD and 10 years of experience has to go through all these sequences, right? So like, if you're the human with 10 years of experience, probably don't want to spend time doing that. And now the models that they have now, the co-folding models, like say from bolts and stuff like that, are much, much better. But they're only obliged to try those things because there's market incentive to, and because there are all these like new like startups that are threatening to compete with them that say that they have all these new drugs. Most scientists don't feel that kind of pressure because most science is not as lucrative as drug discovery. But lots of science is important, even if it's not as lucrative. And so I think people deciding that they don't want to use some specific tool because the hammer didn't work for them, and they have no interest in finding out about it, is a huge loss.
I'm not seeing any more questions. So maybe just to close us out, we've got 5 more minutes, Jordan.
Mm-hmm.
Do you have any recommendations for readings if folks are interested in what you've been saying? Are there sort of other important papers that they could go to or books? Do you have any other recommendations?
Um, Yeah, I mean, I think that there's great literature on this from Kevin Yablonka and Anoop Krishan about just basically the importance of like collaboration in AI for science that combats also the narrative. There have been other papers in the past that say that interdisciplinary work isn't as rigorous as single disciplinary work. And so, I think there are good people pulling the other direction. But I think that the main like the beauty of sort of like this position is just that like the takeaway is that we should just try to bring more curiosity to things that we don't know about. And that's something that we can all like leave and practice today. And I think other than that sort of recommendation for resources that I would point people to, I think are relatively domain specific. In the sense that I actually have not a good sense of what are like, so there's some political scientists in here, but also I have no idea what the landscape of our audience is. And so it's difficult to recommend resources that I think would be, universally appreciable. Hold on, sorry, Mary has a follow-up.
Would you like me to, perhaps I could read it out for the
Yeah, go
recording.
for it. Mm-hmm.
So Mary asks, do you think there's a paradox in developing AI and machine learning tools that might reduce humans' capacity for deep learning and understanding? And if so, can thoughtful design or better research practices help address this issue?
Um, I don't think that there's a paradox in the sense that I don't think getting an oracle lessens your ability to learn other things, or like learn about the system. And maybe even the oracle can help you learn about the system, but the oracle is not the answer. And I think that that's the point that I was trying to make in the talk. But I don't think that the oracle is necessarily an enemy of understanding the system. And insofar as, machine learning as it stands and the tools that we develop right now are sort of like oracles because we don't know what's going on inside them. I don't think that, yeah, is inherently in opposition to human understanding.
Maybe one last one. We've got 3 minutes.
Mm-hmm.
So let's close it out after this one. But again, from the chat, can you please provide some insights regarding whether machine learning domain expertise is recommended and to focus on before delving into AI specific applications?
No, I think you should just go straight to AI for specific applications, like whatever it is you're interested in, because ultimately, like to figure out what's going on in your field, you will have to, eventually figure out what other parts of AI are important for you. I think what happens to a lot of people is they read on Twitter from somebody who's very well-meaning that like, you have to understand the math before you like get into machine learning. And then it's like you have like a 400-page textbook to get through where you just finally at the very end you figure out what ridge regression is, and like nobody is using, I don't mean nobody, but the frontier, nobody is using ridge regression to do anything. And so ultimately you've learned a bunch of stuff, and learning is good in and of itself, but it will not have served you in trying to understand the tools that might be relevant for your work. Um, and so yeah, I mean, I think like no matter what you're researching, basically, like you can probably get a reasonably good start by asking ChatGPT, like, okay, what were the like, most influential papers for this task in the last 3 years? And then trying to read those. And like every time you run into something that you don't know what it is, like get ChatGPT to find you more resources. Now, does that mean you should listen to everything ChatGPT says? No, but ChatGPT is very good at RAG on the internet. And so I recommend it for that.
Thank you very much, Georgia. This is an incredible talk and incredible research, of course, more generally. Wishing you all the best as you sort of build it out, both as at Oxford and also at Hugging Face. And thank you very much for your time. And I hope that you make your flight.
Yeah, I'm sure it'll be fine. Thank you all for your attention and time. And I hope you have a really great rest of your day.
Thank you, everyone. Have a nice rest of the day.
Thanks, guys.